everyone. Welcome to the next quantum computing meetup organized jointly by quantum computing groups from Washington, D.C., Toronto, and Warsaw. My name is Pavel. I'm one of the organizers of the Warsaw Quantum Computing Group meetup and CEO of the Quantum AI Foundation. I will be the moderator today. And we have the pleasure to host a great speaker, Dr. Samuel Chen. He will give us today the lecture titled Advances in Hybrid Quantum Classical Machine Learning. So it sounds very interesting. Before we start, would also like to announce our next meetings. So the next one will be at the end of July, July 29th. And I will be also the moderator. Later in August, Dr. Wong will tell about simulation augmented machine learning for semiconductor physics and defect discovery. Later in August, Henry Liu will give a talk about challenging quantum advantage with classical simulation. And then in September, Dr. Daniel Claudino will give a lecture, Quantum Simulation Based on Expansions of Hamiltonian Moments. Then in October, Professor Vlatko Vedral will give a talk about some open problems in fundamental physics. We'd also like to thank our sponsors, partners for supporting us and making this event possible. And also thanks to Helen for organizing everything. And also thank to Dr. Chen for just accepting our invitation. So somewhere, if you are ready, I think we can start soon, so you can share your slides, or maybe just one more announcement. So recently we had the 6th anniversary of the Washington, D.C. Quantum Computing Meetup. So it's already more than 6 years. All right, let me stop sharing my slides. And maybe just one more announcement before we start. So as you can see, this meeting is recorded. And if you have any questions, please first post your questions on our chat. So we agreed with Samuel that we'll try to make this event interactive and ask some urgent questions, interrupt and ask some urgent questions during the lecture. But in order to just make it organized well, please first post your questions on the chat, and we'll try to interrupt and read the questions if they're urgent. If there are some less urgent questions, we'll keep them for the end and ask at the end during the Q&A session. You can also raise your hand if there is something really urgent, but please just don't unmute yourself and don't interrupt. And I think that's probably all. So Samuel, once again, thank you for accepting our invitation. It's our pleasure to have you here, and we are looking forward to your talk.
Okay, so can you hear me?
Yes.
Okay, so thanks for the introduction invitation. And yeah, I'm very happy to be here again. I think last year, probably the same time, I presented in the Washington, D.C. Quantum Computing Meetup. And this year I will present again in these topics. But in addition to the important things that I already mentioned last year, I will add more things that I have done in the past year. Yeah, so if you attend my talk last year, probably you already know some of the things that I will speak today, but I believe, or I hope you will get some new things in today's talk as well. Okay, and so I'm from Wells Fargo, and prior to joining Wells Fargo, I was at the Brookhaven National Laboratory, and I did the quantum machine learning since 2019. So today I will cover most of the works that I did in the past 4 years. And also I will mention some interesting works from other groups which are related. Okay. And start. So this is the outline for today's talk. First, I will give some motivation of why we study the quantum machine learning and some basics idea of the quantum computing, a very, very basic idea. And then introduce different fields in quantum machine learning. And then I will mostly focus on the applications from classification, sequential or temporal learning, reinforced learning, and natural language processing. Okay. So the machine learning has gained a very significant attention since the success of AlphaGo in 2016, which demonstrated that machine learning can solve very complex sequential decision-making problems. And also the development of transformer-based or attention mechanism-based models are also very amazing. I think I don't need to emphasize how we are impressed by the ChatGPT since last November. Meanwhile, the field of quantum computing has seen significant hardware advancements since 2017, with notable companies such as IBM, Google, D-Wave, and other startups making significant progress. So last November, the IBM announced a 433 qubit system, and as the roadmap shows here, IBM plans to deliver systems with more than 1,000 qubits, and I heard that some other companies also have similar plans. So there are a lot of things that we can expect. So the quantum computing has been shown theoretically to solve certain computational problems with performance superior than the classical computers. So we may naturally ask the following question. So can we combine the best part of both the machine learning and the quantum computing to solve even more complex problems? So in this talk, I will explore the potential of the hybrid quantum classical machine learning, which I will define this term later, and its application in the various applications or probably in industries. And by leveraging the strengths of both the quantum computing and the machine learning, we can probably solve some complex problems that are beyond the scope of classical computers. So I will cover most of my research work in this talk. There are many in the field of quantum supervised learning and reinforcement learning. I didn't do much on the unsupervised learning, so I won't touch that direction. And I will also mention some of the works related from other groups. Okay, so in the quantum computing, it's very different from the classical computers. So in classical computers, we have classical bits, and each classical bit can say either 0 or 1. But at a quantum computer, a quantum bit, or we call qubit, can solve the superposition of both 0 and 1, controlled by the amplitude alpha and the beta. Alpha and beta are complex numbers. So it's very interesting because if we measure the qubit, then it has a certain probability that the measurement outcome will be 0 and a certain probability will be 1. And it is controlled by the alpha square and the beta square. So the alpha and beta are the amplitude, and the alpha square and the beta square are the probabilities. And there is another very important property in the quantum physics or quantum computing. Is called quantum entanglement. So this is a unique property, and there is no analog in the classical computer. And if you study some theoretical papers, and they will show that any quantum advantages or quantum algorithms or quantum machine learning models are based on these quantum entanglements. So this is a very important part. So since the 1990s, there are several important algorithms developed, and probably the two most famous ones are the Shor's algorithm and the Groover's algorithm. So the Shor's algorithm can be used to break the state-of-the-art public key cryptography, such as the RSA, and the Groover's algorithm can provide quadratic speed-up in unstructured database search. But both of these algorithms, they provide a provable advantage, but they require deep circuits, and usually these machines will require the error correction, the fault tolerance, which is not yet available. So what we have now is called the noisy intermediate scale quantum devices, NISQ, and the devices are noisy, so we need a particular way to design the quantum circuit such that we can still use some resources provided by the quantum system. So to learn the quantum physics quickly, so first we need to learn how is a quantum state, and we use the vector to represent a quantum state. So for example, the zero quantum state can be represented as a column vector 1, 0, and the state 1 can be represented as the column vector 0, 1. And usually we can construct the density operators directly from the vectors, and then the probability P is the probability that the system in a particular state, and we can the superposition these states. But usually the quantum operations are just linear algebra matrix multiplication. So after we have the state, the 0 and 1, these are very boring because you will just keep at their state. What we need is a bunch of operations that we can use to move the quantum state in the quantum Hilbert spaces. So there are some states. For example, the simplest ones are the single qubit state. For example, the Pauli XYZ rotation and the Hadamard gate. So so let's have an example, a very simple example. So you have a state initialized at a 0, and then you want to put a X gate, which will just flip from the 0 to 1 or 1 to 0. So when you read the circuit diagram, you read from the left to right. But when you need to write the quantum operations in the matrix form, then you will inverse the direction. So the matrix, the X gate is 0, 1, 1, 0. You put in the left, and then the original state, which is in the column vector 1, 0, should be in the right. And then you just do the matrix multiplication, and you will get the state 1. So this is the X gate or the flip gate, and there are other gates as well. But here we only have 3 or 4 gates, but it's not interesting enough. We want, because the quantum space is much larger than we think, and we can operate or rotate the quantum state vector in the Bloch sphere. So the idea is that the quantum state, a single qubit quantum state, lives in this sphere, the surface, and we need a more general rotation such that we can move the state on the on this sphere. So we need a parameterized gate, and to do this, we need 3 parameters. So this is the most general form of the single qubit rotation gate. And please remember this gate, because this gate is very important. these are the parameters that we will learn using the machine learning algorithms. And if you have some experience in the classical machine learning neural networks, then probably you know the bias or the weights in the neural network. And so you can see these parameters very similar to the weights in the classical neural network. So this is the most general form of single qubit rotation. Sometimes you will use the more restricted form. For example, rotating along axis, y-axis, or z-axis. And in general, the general rotation gate parameterized by 3 parameters can be decomposed into any two of the rotation. For example, x, y, or y, z, or x, z. And also remember that we already said that the very important property in quantum physics is called the quantum entanglement. So in order to entangle the information from different qubits, we need something, some operation to connect them. And the control NOT gate is the simplest one that we can use to entangle information from different qubits. So the C-NOT gate has 2 components. The first is the control qubit, and the other is the target qubit. So the operations on the target qubit will depend on the quantum state of the control qubit. For example, if the control qubit is 0, then it will not have any operation on the target qubit. However, if the control qubit is, for example, 1, then you will trigger the control NOT gate, and you will do the flip operation on the target qubit. So these are the most important quantum operations that we will use in this quantum machine learning applications. Okay, so let's have some idea of what is quantum machine learning. So quantum machine learning can be categorized into 4 categories based on the algorithms and the data they process. So these categories include the CC, the classical data, and the classical algorithm. So this category is not considered a quantum machine learning, but we include it here for completeness. But we can also say it is a certain form of quantum machine learning if you use some quantum-inspired classical algorithm. For example, you use the tensor network to do the classification or other learning, and the tensor network is developed originally to learn or solve the quantum many-body physics problem, or to use to save the quantum wave function. So you can see it as a quantum-inspired architecture. So okay, so we can still categorize it as a quantum machine learning, although it is implemented on classical computers. And for the CQ, the CQ stands for the classical data and the quantum algorithm. So this is the most active research part, and because most of our data are classical, and we hope that there are some quantum algorithms that can help us deal with the increasing complexity and the volume of the data. The QC stands for the quantum data and the classical algorithm. So sometimes this category refers to the subject of using machine learning to solve quantum physics. For example, if you use the classical convolutional neural network to classify different quantum phase transition problems, then it will be in this category. And the final one is the QQ, quantum data and the quantum algorithm. So this category is the most difficult one, as both parts are not yet fully understood. I can give you an example. For example, if you use the quantum sensing, you build a particular sensor, and then the sensor is a quantum devices. So once it sends something, then it will represent a particular, for example, a rotation angle, and then and then this quantum state, you can use a quantum machine learning algorithm to do, for example, reconstruction or classification. So the whole system is quantum. Is usually is very difficult to implement in the hardware, but there are many progress out there. In this presentation, I will focus on the CQ category of the quantum machine learning, which has the most practical applications for industry that dealing with the large data sets. Okay, and so here I need to explain what is the hybrid quantum classical paradigm. If you don't have any prior knowledge of the quantum machine learning or the current state of the quantum computing, then probably you will think that the quantum machine learning is that we have a pure quantum algorithm and we put the algorithm on the quantum computer and you can do all the things, or you can use the quantum computer to log into the Zoom and listen to this talk, or do some very ordinary things. But although in theory, the quantum computer has the same capability of classical computer, so they can solve the problems that the Turing machine allows. But this is theory. Now we only have a very small scale of quantum computer, and some tasks that are very easy on the classical computer are not that easy on the quantum computer at the moment. For example, if you want to calculate the gradient of a particular function, then there are algorithms to do this, but it requires very deep circuits, and it is impractical to do that on the quantum computer. So, for example, if you do machine learning and you need to do gradient descent, etc., so these operations are at the moment best carried out on a classical computer. So the hybrid quantum classical paradigm means that, okay, so we have a computational task and we can divide the task into several subtasks. And some of the subtasks are easier handled on the classical computer, and some tasks are best for quantum computer. For example, if you can show that these tasks can get quantum advantage, then you will put that one on the quantum computer. So usually when the quantum computer, for example, you put the data into the quantum computer and you measure the results, and you can calculate the loss function, and then these values are then put on the classical computer and use classical computer to calculate the gradient, and then output the updated parameter for the quantum circuit, and then you feed back these parameters to the quantum computer and then do the next round, and then iteratively you will have a better and better set of quantum parameters. And after the training, if you want to do the inference, then you don't need the classical computer again. You can just use the quantum computer and you load data, for example, the images of cats or dogs, and then get the result. So this is the basic idea of the hybrid quantum classical paradigm or hybrid quantum classical machine learning framework. Okay, so in this kind of framework, the very basic component is called the variational quantum circuits or the parameterized quantum circuit. So some literature use the parameterized quantum circuit, but they are the same thing. And the idea is that, okay, so these quantum circuits are with tunable parameters, and these parameters are fine-tuned or optimized or learned on a classical computer. So here, since we are considering the CQ, the classical data and the quantum algorithm, so the VQC used in all the works that I will mention today can be represented in this simple form. So first, there is a encoding circuit U of X. So the X is the data. For example, the image pixels, the acoustic signals, the stock prices, something like that, the classical values. And you need to define a particular way or a circuit or an algorithm for the U the U function is a several quantum gates. And the V is the variational or parameterized part, and the theta are the actual parameters that you will learn using the gradient-based or gradient-free algorithm. So
okay, Samuel,
yes.
if I can interrupt, because there is a question regarding the circuit and this learning process. So this is a question from Ron. I think it's quite short. Is this cycle happening once per epoch? I believe that this is a question regarding the previous slide.
Wait a minute. Yeah, so it depends on how the algorithm you design. For example, if you calculate the gradient after every batch of sample, then you need to optimize the model after every batch. So for example, if you have a batch size 4, then you load 4 images and you get the predictions, and then you calculate the loss value, and then you use the classical computer to optimize the quantum circuit parameter after a batch. Or of course, you can put, so if you have a large enough system, you can definitely put the whole data set in a single batch, right? And then you can calculate the gradient after a single epoch. It depends on the optimization routine that you choose. Okay, so let's continue. Okay, so here the V is the parameterized or variational circuit, and the theta is the parameters that we will learn. And you can see this theta, the analog of the classical neural network weight. Okay, so let's have a very simple example of how the variational or parameterized quantum circuit works. Okay, so we always start the system from 0 because it is the ground state of the quantum system, and here we have the Y rotation gate parameterized by the phi angle. And so if you just write out the matrix multiplication in the previous slides, then you will get the column vector of cosine phi over 2 and sine phi over 2. Okay. But the phi usually, when the system starts, just like the classical neural network, it is a randomly initialized number. So if you want to classify image, probably it's not the best choice. Okay, but if we do a very small change of the phi from phi to phi plus delta phi, then we may also have a small change in the output from the system. So let's move forward. Okay, so we have the theta here, which is the encoding gate. You can see that you put the pixel value in the theta, and you put your learnable weight in the phi, and then you do the measurement. So let's write out this circuit diagram in the matrix form. So if we do the matrix multiplication correctly, we will get this column vector, and then these values are just the amplitude of the for the state 0 and the state 1. So if you measure the system, you will get probably the state 0 or 1. You will get just one case, either 0 or 1 with certain probability. So here, the probability means that, okay, so if you measure the system only once, then you will only get 0 or 1. And if you don't do, if you didn't prepare the circuit again and then run, you will never know the actual distribution. But if you prepare the system and run it again and again, and you collect all the results, then you will find out that the probability of the measurement outcome in the 0 and 1 will follow this distribution. Okay, so with this in mind, we can use this to do classification. For example, if we only measure one value and if it is closer to zero, I mean the expectation value, if it is closer to zero, for example, below 0.5, then it's cats, and it's above 0.5 is dogs. Then we can compare this with the ground truth, and based on the information, we can update the parameter, right? And then again and again, we will have a better approximated the classification model. Okay, so how can we compare with the target? So you already know the classical machine learning is the loss function, and there are different kinds of loss function. If you are approximate, for example, do the regression, then probably you will use the mean square error loss. And if you are doing the classification, then you will use the cross entropy loss. So this is the loss function. And how to update the parameters? We can use the gradient-based method, for example, the stochastic gradient descent, or you can just also use the gradient-free method, such as evolutionary algorithms. And the U of X, the encoding circuit, is very important. The purpose of that circuit is to represent the classical value in the quantum state. And for example, if you have an n-qubit system, then the quantum state can be represented as the linear superposition of the basis state. And the C of Q1 to Qn are the amplitudes, and the quantum encoding circuit is trying to transform your classical values, such as the pixels, signals, time series values, into this amplitude. And there are different kinds of encoding method. And for example, the amplitude encoding. So if you have an n-dimensional vector, then we can use the log to n amplitudes to represent a log to n qubit system to represent this amplitude. However, since the amplitudes they need to their square sum need to be normalized to 1, so you may lose some information during the normalization. And another method is called the variational encoding. So the variational encoding, there are a lot of different kinds of encoding method in the variational encoding, but the basic idea is that, okay, so you use your input value as the rotation angle, and probably the input values may undergo certain kinds of transformation. For example, in this example, we use the arctangent or the square to transform your input value first, and then use this input value as the rotation angle. So in this way, you can encode your value into the quantum circuit without a very deep circuits like the amplitude encoding. I heard that there are some questions. Or I can continue.
No, I think you can continue, because I don't see any questions on our chat. There are still some new people coming, so it's possible that someone just forgot to mute themselves.
No problem. Okay, so so in this hybrid quantum classical paradigm, so we can combine multiple components in a way such that a directed acyclic graph is formed. And so different classical neural networks or quantum circuit can be combined into a very complex model. And in general, the whole model can be trained in an end-to-end manner. And in the output part of the whole model, usually we will process the system with some loss functions. For example, the cross entropy for classification and the mean square error for function approximation. So in the classical deep learning, we already know that we can use the backpropagation to train a very, very complex model. with billions of parameters. And so the natural question is that can we use the same idea in this hybrid quantum classical system? And the answer is yes. So we already know how to calculate the gradients of a classical node. So the next question is how to calculate the gradients of a quantum component. So if we know how to calculate the gradient of a quantum node, then we can optimize the whole hybrid model. So so let's start from a very simple case. So we have encoding gate U0 of x and some small rotation gate parameterized by theta. So as I mentioned earlier, the system starts from 0 and then encode and then variational gate and then the measurement. And if you write it out mathematically, you can have the following representation. So what we want to do is to calculate the gradient of this quantum function with respect to a particular parameter. And it is shown by a very important paper from Osaka University that the gradient of the system, the quantum system with respect to a particular parameter theta I can be represented as this. And this is the exact formulation. It's called the parameter shift rule. So you can see that if you want to calculate the f of x with respect to the parameter theta I, you need to run two circuits. One the theta I plus pi over 2 and the theta I minus pi over 2. So that's why it is called the parameter shift rule. If you are interested in the proof, then they provide a proof. It's just probably 3 to 4 lines. It's very simple, but it's very important one. And one thing that I need to remind you is that this is different from the finite difference method, because there's no infinitesimal elements there. So numerically is much more stable. Okay, so now we know how to get the gradient information of the quantum circuit, and then we can combine all the things together. And in the classical neural network, we have the automatic differentiation. So for example, if we want to calculate this very simple hybrid model, then we can use this the forward pass method. For example, when I want to calculate the f of xyz with respect to the x, then when I evaluate the function, at the same time, I can calculate the, for example, the dx over dx and the dy over dx, and I store the information in the memory. And then when in the next step, v equals x plus y, when I calculate this step, I can use the Chen rule to get the value of dv over dx, and then I can store the information when I evaluate this function. And when I get the final result of the this function, I also have the gradient of this function with respect to a particular parameter that I want to get the gradient. So this kind of hybrid quantum classical framework can be implemented using these famous open source packages such as the Qiski, TensorFlow Quantum, Panida, and the Torch Quantum. So these are all very good packages that you can use for free. Okay, so I will let's get into some applications. So probably the most straightforward application is the classification. So this is from also the Osaka University, the paper which proposed the parameter shift rule. And in this paper, they provide this kind of variational circuit, and they use this variational circuit to classify this very simple data set. I think it's called the concentric circle in the scikit-learn. So the left-hand side in the left is the data set. So there are blue and the red dots, and the model is trained to classify the system, and it is very successful. But if we want to study more difficult classification tasks, such as the images, then we may need a more complex model. And in the classical machine learning, we already have the convolutional neural network. The convolutional neural network, the idea is that there are several filters or kernels, and these filters or kernel will scan over the images and then extract the information, and then use this information to pass through to the next layer. And so you will get different layer of abstractions or blur the input. So how can we use the quantum circuit to do the CNN? So we can use the quantum circuit, variational quantum circuit, to do the task that the classical kernels or the classical filters do. And for example, if we have a 2x2 kernel or a 2x2 filter, then we can build a 4-qubit quantum, a variational quantum circuit. So in this paper, we consider a event classification problem. But okay, so there are 4 different kinds of the events there, and in the upper panel there are several examples, but you don't need to know any particle physics. You just need to know that there are different types. So there is no fundamental difference of this task and the digit recognition or the CATS virtual stock data set. So what we showed here is that if we constrain the number of parameters to be very similar in both the quantum and the classical CNN, then numerically we can show that the quantum version of the CNN can reach a better accuracy, or it can learn faster than the classical models. The faster here means that using a smaller number of training epochs. Okay, but we have the classification system, and you can say that, oh, we can use this system. If we have a larger quantum computer, we can do a much difficult task and do for example, the medical images or other finance or other applications. But usually these tasks include some sensitive or private data, and usually the users or the institutes don't want to share their data. So it's very difficult to use a centralized system to process all these data. So there is a idea called federated learning. So if we have a lot of participants and each of them has their own data, and we want to train a bigger model, but each of the party doesn't have enough data to train a capable model. So they must collaborate, but they don't want to share their own data. So a way to do this is that, okay, so you train your data locally, and then you only share the trained model or the model information to a central server. And then a central server will have a particular way to aggregate this model and then distribute the aggregated model to all the participants, so they can collaborate without sharing their private data. So we try to study this framework in the quantum area, and we try this CATS virtual stock data set. But there's one question. So the image is around 200 by 200 dimension. It is very easy to for a classical CN to do this, but at the moment it's difficult for a quantum computer to process this dimension of data. So we need a way to do dimension reduction to shrink or compress the original input into a scale that the quantum computer can process. Well, so we use another transfer learning idea. The idea is that we have some pre-trained classical models. For example, the classical convolutional neural network, or for example, the VGG16, or others. And we use these classical convolutional neural network to first compress these CAT's image into a smaller dimension, for example, 4-dimensional vector, and then use the quantum circuit to do the final classification. Yeah, so you can always challenge this idea that probably the classical neural network already do most of the task. Probably you are right. Yeah, but as the quantum system gets bigger and bigger, sometimes probably sometime in the future we can just drop the classical pre-trained model or the classical pre-processing model and then use the full quantum computer to process the images. But we just want to use this as a prototype to demonstrate the potential of using federated learning in the quantum machine learning. So we distribute these data to a bunch of participants or the clients, and then they use these data to train their local quantum model and then share the quantum model parameters. And then the central server will aggregate. The aggregation is very simple, just the average of all the models, and then distribute the aggregated model to all the participants. So we try this kind of federated learning, and we can show that although we use a smaller number of data, it still reach the performance or the accuracy when we use the full training set. Oh, I found there's a question.
Yes, so we have two questions on our chat, but they seem to be quite general, but I can see that Itamar has raised his hand. So Itamar, if you have question related to the current slides, then feel free to ask.
Yes, I have a question. It's fantastic, all these examples. Do you hear me?
Yes.
And the question is if Qiskit or you or somebody can build a library that covers all possible problems that are in these examples and others, and I can use them as a black box, not even need to understand quantum mechanics or quantum computing.
I think we are not there yet. So there are some good packages. For example, the Pennyland and the Torch Quantum may be the closer to what you want, but at the moment we still need to define your circuit ansatz because it depends on your tasks. So there is no single best quantum circuit for all the problems. Just like you don't have a single neural network for all the tasks. Okay, so let's continue. So we use the federated learning on these hybrid quantum classical models, and we can show that the aggregated model can reach similar performance if just like we train the whole model centrally with all the data. And I want to emphasize here that although we have 100 participants in the system, at every training run or every airport, we the global airport, we only randomly choose 5 clients from out of the 100. So at each airport, effectively we use a much smaller amount of the data to train the model. So it looks like this work points a promising direction that we can use an array of quantum computer to train a big model efficiently. And at the same year, another group from the Virginia Tech, they use a very similar idea of the quantum federated learning. However, they are dealing with the quantum data. So here they are not dealing with the CATS virtual stock data set. They are trying to classify, for example, the quantum state or other quantum stocks. And in the quantum data set is basically the circuit parameters, and then you can use these circuit parameters to generate a particular quantum state, and then use the machine learning model to classify those quantum states. This is also a very interesting work, as it can provide another application of the quantum federated learning, and this may have some implications in the distributed quantum sensing, for example. Okay, so once we have the classification, the next part is to do the sequential learning or learn a function. So so in the natural language processing, the model needs to process a significant amount of text strings, or in physics, the dynamical data are usually recorded in the sequential form, such as the time evolution of a quantum system. And in the forefront of the reinforcement learning, also depends on certain kinds of memory to keep track of the trajectory, which is crucial for the agent to make better decisions in later steps. So in light of this, our goal is to study the machine learning architectures, quantum machine learning architectures, such that we can predict time series more accurately. So let's get back to the very basics of the function fitting. So in the very original form of the quantum circuit learning, we can build this variational quantum circuit to learn simple functions such as y equals x squared and y equals absolute value of x, or y equals to exponential x. These are simple functions. And but what if we want to learn more complex dynamics or other, even the language? It's not as simple as the y equals x squared, right? So we need a particular method that we can use to memorize, or probably have the information of previous steps. And so we can learn a lot from the classical machine learning. So in the classical machine learning, there is a method called the recurrent neural network. So what makes the recurrent neural network different is that in each time step, they output not only the values that we can use to evaluate the performance of the model, it also output another value, which will be fed back to the model in the next time step. So in the next time step, the recurrent neural network will also have the information of the previous time steps. And this makes the neural network based model possible to to keep track of previous information. But the original design of the recurrent neural network suffers from some issues such as vanishing gradient or vanishing exploding problem, or it's very difficult to learn longer temporal dependencies. So there is a updated form of the recurrent neural network called long short-term memory. So it includes some other cell states and hidden state to keep track of the long-term dependencies, and also have more stable numerics. So it partially solves the vanishing or exploding gradient problem. So so the next step is that, okay, so we know the classical LSTM, and can we build a quantum model in this direction? So if you look deeply into the classical LSTM, so you need to
Look at there.
I think we can go on. So
Okay.
a new person joined, but I think that he's muted now. Okay.
Okay. So if you look closely into the classical LSTM, you will see that once you get the hidden information from the last time step and the input from this time step, you need to copy the values to 4 different neural networks. This is very easy in the classical computer, but if you encode the information into the quantum state, you cannot copy or clone the quantum state easily. So in our design, we still use the 4 variational quantum circuit to replace the original classical neural network. And then since the input data, the H hidden state and the input value from this time step X, T, they are still classical values. So we can copy them first and then input to the 4 variational quantum circuit. So the idea is very simple. We use the VQC to replace the classical neural network. And we want to find out if it is better than the classical LSTM. So if we, for example, if we study different functions, for example, the damped simple harmonic motion or the Basel function, which are very common in the class in the physical dynamics, we can see that if we consider the quantum and the classical LSTM with similar number of parameters or similar model size, then the quantum LSTM can learn the dependence or the systems with a very small number of training epochs. So that's the empirical advantage that we can observe in the quantum LSTM. But there is a challenge. So training the recurrent neural network, both classical and quantum, requires the backpropagations through time. So you need to unroll the neural network in the time axis, and you need to calculate the gradients on the time. Usually this is a very time-consuming task. Calculating gradient in this direction is not easy. If you have a very long sequence, then it's even more difficult. So you may ask a question that, can we use some idea of the recurrent neural network, both quantum and classical, but we don't want to train all the circuit parameters? And the answer is yes. There is a field called the reservoir computing. So you need to have a reservoir, and this reservoir is usually a physical system, probably just a reservoir of water, some the superconducting qubits, or more abstractly the recurrent neural network. the classical recurrent neural network. So you can use the classical recurrent neural network to map the input into a high dimensional spaces, and then the reservoir will output a bunch of values, and then you just train a simple linear classifier or linear regression layer at the end of the reservoir. So you don't need to touch the parameters or the configurations in the reservoir. You just train the model which process the output from the reservoir. So it will save a lot of time, right? So you don't need to actually train the classical neural network. So it has been shown that the classical neural network can do this, but can we use the quantum recurrent neural networks such as the quantum LSTM or other quantum recurrent neural network to serve as the reservoir? If we can do this, then we can use the good property of the quantum recurrent neural network without training all their parameters. So we use the quantum LSTM again, but now we turn off the training or the gradient calculation of those variational quantum circuit. We only train the classical layers after the quantum LSTM. So that's a part of the result. So here we consider the QLSTM RC, the reservoir computing version means that the QLSTM are not trained, and the QLSTM and the classical LSTM RC. Here again, we limit the number of parameters or the model size to be very similar. So we can see that the QLSTM RC and the QLSTM they perform very similar. But in the final 100 epochs, the QLSTM learn fits the functions better than the QLSTM RC. I think it is within expectation because the QLSTM trains all the parameters, so it has more capabilities. But for the QLSTM RC, we just train the final classical layer. We didn't touch the value or the parameters of the QLSTM. It saves a lot of time in the training. And also we found that the QLSTM RC is better in learning the functions than the LSTM, classical LSTM reservoir. So we show again the empirical advantage of the proposed quantum models. Okay, so the next application that I want to cover is the reinforcement learning. So the reinforcement learning is a type of machine learning techniques that the agent learn how to make decisions in an interactive environment by trial and error. So we already covered the supervised learning in the past several slides, and now we will cover the reinforcement learning. So the basic idea of reinforcement is this. So there's an agent. So the agent may be a classical neural network, or a quantum circuit, or some other thing. And there's an environment. The environment may be a video game, maze, autonomous driving, or trading, etc., etc. So the agent will execute an action A of t at time step t, and the environment will evaluate how good or how bad the action is, and then feedback the reward and the current state of the environment. So here the reward is a scalar value. So if it is a good action, then the environment will feedback a positive reward. Otherwise, it will be negative. So the agent is the goal of the agent is very simple. It's just to maximize the total discounted return. So for example, if you play a video game, what you want to do is to maximize your scores when the game episode ends. So let's get back to our hybrid quantum classical paradigm. So again, we have a quantum circuit or quantum computer here, and it can interact with the environment. But now we still need another classical component to help quantum learning. So the classical computer again is the optimization routines such as the gradient method, or if you want, you can use finite difference or other evolutionary methods. So in the quantum computer, we can construct a particular quantum circuit to solve the task in mind. So it requires some knowledge to design a good encoding scheme for a particular environment that you want to solve. For example, in this very simple example, the agent starts from the S, and the goal is to go to the goal G, and the agent cannot step into the hole. Okay. So now we have 16 states, the 4x4 matrices, and we can have 4 qubits, and we can encode these binary values into the system, so you can construct a particular circuit architecture such that you can encode from 0000 to 1111, the 16 states. And then we can show that in this very first quantum reinforcement test, we can use the quantum circuit to be the agent which can after the training, which can go from the S to the start point, the goal. But this is the very early or simple example. How about using the quantum reinforcement to solve a more challenging task? For example, the environment more difficult that requires the agent to memorize previous information, or if the environment is only partially observable, means that the agent cannot access all the information of the current status of the environment. So in that case, the agent may need to keep track of its trajectory such that it can use those old information to make decisions. So as we already learned, we can use the quantum recurrent neural networks such as quantum LSTM to learn the sequence, to predict the time series. And can we use the similar model in the reinforcement such that the reinforcement agent can keep track the information of the previous time steps? So we follow the similar algorithms in the last the reinforcement in the deep Q learning one, which can be used to train the agent working on the a very simple maze problem. So here we consider this carpal problem. So this now the situation is a bit different. For example, the input to the system is 4 dimension, and they are continuous values because the input information includes the for example, the velocity or the angle of the pole. And so it is a continuous input, not a discrete input. So it's more challenging. And in the partially observable cases, we drop one of the dimension of the observation vector, so that the agent cannot access to all the information of the carpal system. So you must have an ability to make decisions based on its previous information. So we compare the QLSTM based model and the LSTM based model in this deep Q learning setting. In the upper panel, I show the number of the parameters in both of the system, and we can show that even the quantum LSTM system with a smaller number of parameters, it can provide a higher or a more stable scores after the training. And then we want to study other part of quantum RL. So why? Because the gradient methods may suffer from local optimum, and probably you can never achieve the good results. And certain quantum reinforcement models are very difficult to train using the gradient-based method. So in the classical reinforcement, evolutionary optimization has been used to optimize the model, and sometimes it can beat the gradient-based method. So what is the evolutionary the quantum reinforcement? So okay, so we initialize a parallel instances of the agents, and then we use these agents to play against the environment, and then we can get their scores, and then we use the top performing agents to generate the next generation. So the idea is so simple, and we use this to, for example, solve this couple again, and it looks like we can reach a very high score, and then we want to solve a more challenging test, for example, this grid navigation test. So this is different from the couple and the frozen lake that we just mentioned. So in this environment, it has 147 dimensional vector, and so it's much larger than the quantum machine learning model can handle. For example, you have only a bunch of qubits, and you cannot just load the 147 dimension using the variational encoding method. And another thing is that in this environment, the agent will get the reward only when it reaches the goal. So it is a sparse reinforcement problem. So the gradient method sometimes will fail. For example, at least in the quantum reinforcement is a big challenge to solve this environment easily. Okay, but the first challenge that we need to solve is the high dimensional data. How to deal with the 147 dimension. So you need a way to do dimensional reduction, and we already mentioned that you can use the pre-trained convolutional neural network, for example, or other trainable and non-trainable methods such as the PCA, or just downsampling the vector, or using some trainable methods such as neural network or the tensor networks. So we choose the tensor network as it is a quantum-inspired classical method, and it has been shown that in certain classification tasks, it has better performance than the neural network. So we use a tensor network, particularly the matrix product state, to be the data compression routine, and we can put in for example, the 147 dimension vector, or probably images if you want, and use the tensor network to generate a compressed representation. And then the compressed representation can be further processed using a quantum computer. So the whole model can be trained in end-to-end. So now this time the tensor network is not a pre-trained model. It is also initialized with the random parameter, and then you connect it with the variational quantum circuit, and you form a directed acyclic graph, and the whole model is trained using the you can use the gradient-based or gradient-free method. For example, the evolutionary optimization method. So the tensor network is that you can approximate a large matrix using the smaller matrix products, and then you map your input dimension, and then you use the MPS to process your input data. So the whole model for these hybrid tensor network variational quantum circuit model is that we have a tensor network, and we compress the 147 observation to a qubit or 8-dimensional vector, and then the 8-dimensional vector can be further processed using the VQC. And then we use the aforementioned evolutionary optimization method to fine-tune the parameters of both the matrix product state, tensor network, and the quantum circuits. And then we show that in all the cases that we considered, this evolutionary hybrid model can be the classical model. So it is a very effective way to do this, and since since in each generation we use the parallel agent, so it can be scaled up if you have a large scale computing resources or many quantum computers. But in the evolutionary method, we still need to we need to wait all the agents to finish their round and then calculate their fitness or their scores, and then to decide how to generate the next generation. So is there any better way to do the parallel training? So there is a way called asynchronous training from classical machine learning. So the idea here is that, okay, so we have those parallel instances, and those agents are interacting with their environment, and then learn how to make decisions, and then they calculate their gradients locally, and then they share their gradients to the global model. So you don't need to wait others to finish. When you finish, you just upload your gradients, and the global model will use your gradient to update the global model and then send back to you. And when the other agent finished its own part, it will upload its gradients, and then the global model will be upgraded again. And so if you have a bunch of these agents, then and since you don't need to wait all the agents to finish, so that you can move to the other episode. So it will be much efficient. And also you don't need to use for example, the replay memory to reduce the correlation or the correlation of the trajectories or the sampled observations. So it's very fast, even faster than the evolutionary method that we just mentioned. And it can be used to solve those classic methods, for example, the alphabet, the carport, and again the navigation problem. Now it's more difficult because the agent need to find a way to cross the different rooms to find the goal. The goal is in the green boxes. So we can show that if the task is not difficult enough, then the classical model can beat the quantum one. But when the situation gets more difficult, then the quantum model can perform well. And there are other similar and follow-up works in the quantum reinforcement. I recommend you to find some of these papers if you are interested in this area. And the final applications that I want to mention is the natural language process. One part in the natural language processing is the speech recognition. And the speech recognition is a very important area. Not only because it is very something that is very convenient, but also it requires a very special design to keep your privacy. And for example, in this kind of vertical federated learning, so originally the federated learning I just mentioned is the horizontal, but this is the vertical federated learning. So your speech input are first processed into a spectrum, mail spectrogram, and then you send to the quantum layer. The quantum layer are randomly initialized quantum circuit and quantum gate. And this quantum circuit will process your your speech signal and then encode it into a particular vector, and this vector can be further processed by other, for example, the classical algorithms, and using the random quantum circuit to process first can prevent the model parameter leakage. And another interesting application is to use the language models to extract or embed your language information, and then after the embedding, using the temporal convolutional kernel, quantum temporal convolutional kernel, to process the embedded vectors, and then use this information to do, for example, the final classification test. And for example, in this paper, the authors use different data set and also compared with the more traditional word to vector embedding, and then the more modern BERT embedding, and then also compare the classical temporal kernel or the quantum temporal kernel, temporal convolutional kernel, and we can show that the quantum cases beat the classical one, and also the BERT is better or word embedding framework. And a more recent work in the quantum language model that I want to mention is from I think it's from the Johns Hopkins. They use the quantum LSTM to process the text data, and the data set that they choose is the Twitter data set, the multilingual Twitter data set, and they can deploy the quantum LSTM language model in the cloud and use this cloud-based quantum model to do the sentimental analysis, and this is also another kind of vertical federated learning. So we can expect that more and more quantum computing-based language model will be proposed in the coming years. Although there are still many limitations in the quantum computing architectures, devices, or number of qubits. So probably you cannot beat for example, the ChatGPT right away, but there are many promising developments out there. So in conclusion, the hybrid quantum classical paradigm is something that we use classical computers to optimize the quantum circuit parameters, and we put only the computational task that we can get quantum advantage on the quantum computer. We still use a lot of classical computer to help the quantum computing tasks. And the variational quantum circuit or the parameterized quantum circuit is the building block of the modern quantum machine learning applications. And the VQC can be combined with different kinds of classical models or quantum-inspired classical models in a very complex way, and the whole model can be trained in an end-to-end manner with both gradient-based or gradient-free method. And the whole system can be trained using the automatic differentiation. VQC models are very successful in different kinds of tests, such as classification, federated learning, or privacy-preserving AI, or function approximation, reinforcement learning, natural language processing, such as speech recognition or language model sentimental analysis, etc., etc. There are a lot of interesting things out there, and yeah, we expect there will be more, probably more realistic applications of quantum machine learning in industries or other more challenging real-world data sets in the future. That's my talk for today, and thank you for your listening.
Okay, great. Thank you, Samuel, for this great presentation. We have several questions on our chat, so let me maybe start from the question asked by Hernan. When we want to prepare these parameterized circuits, there are some important aspects that we should take into account, such as expressibility and entangling capability. How can we know if the ansatz we have prepared is optimal in terms of expressibility and entangling capability?
Wait a minute, let me scroll up.
Okay, yes, it was asked at quarter to 2 p.m. by Hernan Dario.
Okay. So okay, so I think this is very difficult. So there are some theoretical tools to characterize the entangling capacity or the expressibility. For example, the how the model can be used to represent particular functions or function families, etc., etc. But I believe that it is still very difficult in the practical perspective. So, for example, given a imaging classification test or a functional approximation test, for example. So I believe that now it is still very difficult to determine if the model is optimal before you ever train the model.
All right. Good. There is another question that was asked on YouTube. Are there any practical applications of quantum convolutional neural networks or any quantum classification that replaces the classical approach?
So as I already mentioned, so if we have some constraints such as the number of parameters or the model size, then usually the quantum models can learn the optimal classification with a smaller number of training epochs. And I know that some other theoretical works also mentioned that those VQC-based model can learn a distribution with a smaller data set.
Okay, good. And how about the quantum advantage of quantum LSTMs over LSTMs?
So again, if we limit the model size, then usually the quantum LSTM can learn the pattern of the function with even a single training epoch.
Okay.
But I need to mention that if you use a very large model of LSTM, then it will still beat the quantum version. For example, if you use a model with probably millions of parameters, then I believe it will still be the quantum model with hundreds of parameters very easy.
Okay, great. I can see another question from Berend this time. Just wondering, when using random numbers for the evolutionary approach, would there be a difference between classical randomness and the true quantum randomness?
So here the parameters are for the quantum rotation angle, and by its nature, it's still a classical number. In this initialization part, I think is very similar to the classical evolutionary method for the classical deep neural network. We haven't touched the initialization of those parameters with quantum approach. For example, you can use the quantum random number generator to generate the parameter. That's something that probably we can study in the future.
Okay. There was also another question on YouTube about the related code implementation available for quantum recurrent neural networks and quantum LSTMs. I believe that there are such repositories on the internet, but maybe
Yes,
someone has
I
some
know what.
recommendations.
So there is an open source package called Torch Quantum, and if you find their GitHub repository, they have some examples, and quantum LSTM is one of the examples.
All right, good. Another question from Emin Akpinar. Because of the NISQ quantum computers, especially in image classification problems, when the number of images are large, the pixel values of the images should be reduced as much as possible in quantum machine learning. To overcome this, is there any method that we can use in quantum machine learning different from classical dimension reduction methods?
So I believe that the best way to reduce the dimension is using the amplitude encoding in the quantum machine learning. However, in the NISQ area, the amplitude encoding is very challenging because it requires a very deep circuit to encode the input. But theoretically, it is a very good method. So if we have a more reliable or fault-tolerant quantum computer, then amplitude encoding is a very good way to load large dimensional input into the quantum computer.
Okay, I can see that Itamar has raised his hand, but let me maybe ask the last question that I can see on the chat from Ron. In classical machine learning, parameter weights are randomly chosen before training runs. Are there quantum computing algorithms that could calculate smarter starting weights? It's one of the last questions from Ron.
This is a very interesting question. I know that there are different kinds of parameter initialization algorithms out there. They want to use those algorithms to initialize those quantum parameters such that the models may escape the barren plateau issue. So the barren plateau is a very serious or critical problem in the quantum machine learning because when you increase the number of qubits, for example, the model will quickly face the vanishing gradient problem. And if as you know, if the gradient is very close to zero, then the model will not learn. So yes, so there are different kinds of works out there try to initialize smarter parameters.
Okay, there are some new questions on our chat, but I think that Itamar was first. So Itamar, please go ahead.
Do you hear me?
Yes, we can hear you.
Okay, sorry, I'm on the road. If there will be noise, ignore it. So my question is, we are talking hybrid, and can you see a point in doing iterative cycle between classical and quantum, where each informs the other, and in some kind of cyclic way, for example, difficult problems like dimension reduction that was mentioned, and I can see many others where, like you mentioned, that the quantum requires less parameters. So I can run in parallel the quantum and the classic, and one can fit the other in terms of reducing number of parameters. Am I clear? Hello?
Yeah, can you state your question again?
Okay, take a problem like T-SNE or UMAP, where I want to reduce the dimension. Now, if the quantum requires less parameters, I can run the problem first on classic and then see what the quantum can do better, and then repeat this iteratively in a way of ping pong, you know, and if you hit me hard, I can hit you harder if I'm a good one, and so on.
Yeah, I
Is
think
this
it's I think it's something doable. I believe that there are works using the for example the transfer learning or the knowledge distillation. So you can use the either quantum or classical train the model and then distillize the knowledge to another one, and then and probably you can shrink the model.
Itamar, does it answer your question, or do you maybe have a follow-up question? You are muted now, just in case. We cannot hear Itamar, so let's maybe go to the other questions on our chat, and maybe we'll come back to Itamar later. So there are some questions about the slides, but they have been already answered by Helen. And there is a question from Dev. Yeah, quantum machine learning. So this is the last question on our chat. Yes, that's the last question. Quantum machine learning use the measured data of quantum state, but basically quantum measurement is unique due to quantum state collapse. So I think we can apply quantum machine learning approach for single measurement experiment or single photon experiment. What can be said about this?
So although much quantum machine learning method use the repetitive measurement, I mean the prepare the circuit again and again and do the for example z expectation value and then get the expectation value to do the inference. But I believe, and I mean there are some other quantum machine learning frameworks using only the very small number of measurements or even the single measurement. So if you want to do the single measurement experiment, then probably you need to use those kind of quantum machine learning methods.
Okay. Yeah, Itamar is unmuted now. So Itamar, would you like to?
Yeah, now I am in a void that I have to put my mask. I hope you still can hear me.
Yes, we can hear you.
I may be repeating myself, so sorry for that. I'm looking at some cycle, iterative way, ping pong between classical and quantum, more than one round, like improving all the time. Was this clear or interrupted?
Well, I believe that the
Chen, you are unmuted, so try. Yes.
Okay, can you hear me now?
Yeah, now it's okay.
Yes, okay.
Yeah, so I think you can consider different kinds of the generative adversarial networks, but this time you use the one party is the quantum and the other is the classical, so they can beat each other.
Okay, good. All right, I've just answered one of the previous questions. Let's see, what do we have here? I don't see more questions on our chat. Do we have more questions now, or maybe someone would like to raise a hand and unmute?
Maybe
Yes?
can I give one question, because what you said about quantum machine learning, your examples was strictly connected with tabular data and this kinds of stuff. Do you know that any processing for graph kinds of data, or because graph computing now is very popular also for machine learning and deep learning methodology?
Yes, indeed, there are a lot of graph convolutional neural network in the quantum, and there are different kinds of methods. So last year in this talk, I covered one of the papers that use a hybrid way to classically transform classical data into something like an image, and then encode it into a quantum state. And there are other kinds of wave encoding such that you can encode the graph directly on a quantum circuit with different control gates. So for example, if you have say a 4-node graph, and then use a 4-qubit system, and then you use the control NOT gate to connect okay, so you map the node into the qubit, right? And for each connection, you use the control NOT gate to connect. So yes, so there are works in this direction.
Yeah, thank you.
Okay, there's another question from Kevin. Can you explain in more detail how quantum tensor network works and how it fits in machine learning?
So this is a very big question. So the actual working principle of the tensor network. Okay, so I think that you can see this. So for the machine learning, either the quantum or classical, we basically build a matrix, and the matrix is operating on the input vector, and then we'll generate a smaller, much smaller dimension of the matrix, and then a vector, and then we use the vector to output the result. Okay, so there are different ways to approximate this big matrix. So the assumption is that there is a perfect classifier problem. Imagine that there is such classifier, very big matrix, but we don't know the answer, right? So we can use different kinds of method. For example, if you use the classical neural network, then you use the different matrix multiplication to approximate that big matrix, or you use the quantum circuit, then you use the unitary matrix to approximate that matrix. And if you use for example, the tensor networks, then for example, the matrix product state, then actually you use the product of a lot of smaller metrics to approximate that matrix. So I think the idea are very similar, but with a different approach. But the detail, I think it deserves reading some tutorial or review papers to get how these different kinds of tensor network. I mean, even in the tensor network, there are different kinds of the way to approximate a big matrix or a quantum state or a dynamic system, and there are some technical details there.
All right. Thank you for answering this question. And I don't see more questions on our chat now, so let's maybe wait. Maybe there will be a few more questions later. Itamar has his hand still raised. So Itamar, would you like to ask another question or?
Yeah, I just want to thank the speaker very much, and it's wonderful talk. Thank you.
Thank you.
Great, thank you. Yes, we have very positive feedback there are many thanks and congratulations on our chat. So wonderful. Okay, I don't see more questions now, so I think we can conclude. So Samuel, thank you once again for, first of all, for the great presentation and also for answering all the questions. So that was also very interesting and fruitful discussion. I believe we've all learned a lot. And we'd also like to thank all the participants. We've already announced our next meeting. So the next one will be at the end of July. So we hope we'll meet then again. And I think we can finish. So Helen, I think we can stop recording. All right. So thank you once again, everyone. Have a good afternoon and evening, depending on where you are. We hope to see you next time. Thank you.